All right. Well, I'll begin with a word of prayer. So, Dear Father, we thank you for this day. Thank you for this class. Just ask that you bless our work today. Help us to glorify you, what we do, and understand a little bit more about matrices, Lord. In your name I pray, Lord Jesus. Amen. All right. So, if there's any day you have to do this, it's today, obviously. So, I just lost 20 subscribers, but I probably gained 30 more. So, that's what happened last time anyway. But, okay, so, matrices. So, definition. A, an element of R, M, N means A is equal to A11, A12, A1N, A21, A22, A2N, AM1, AM2, AMN. So this is a M by N matrix. An M by N matrix. So what we're looking at is, M rows and N columns here, where Aij is an element of the reals for 1 less than or equal to I less than or equal to M, and 1 less than or equal to J less than or equal to N. So some terminology that we should know. Here, I is a row index, and J is a column index. So this is a matrix. A matrix is a box of numbers, basically. All right? And, of course, we could also talk about matrices that had entries that were not from the reals. Like I could talk about, so like remark. Let me just make this quick remark. My notation is this, guys. SMN is set of M by N matrices with entries in S. So this right here is the entry, an entry of the matrix, or more often we call it a component of the matrix. So the components or entry of the matrix are numbers, but the matrix is not a number. It's a box of numbers, all right? So, so my next definition, well, I guess I should say a little bit more here about that. Let me bad choice of location there. All right, there we go. So here, this matrix A, we could also write, let me see here if I can say this. So you could also write this as like column 1 of A, column 2 of A, all the way out to column N of A, like that. All right, so column 1 is this piece right here. This is column 1. So we can look at a matrix as being, a concatenation of its columns, and we can also look at the matrix as being a stack of row vectors. So this is like row 1 of A, row 2 of A. There are M rows, row M of A, all right? And so like for example, the first row of A is where it's these guys right here, right? So I can give a little bit more definitions for us here. Like, okay, so I can write it this way, right? But it's also good to just, try to write a formula for it. So if we look at the, let's say the jth column of A, right? And we look at the ith component of it, what is it equal to? If we look at the ith row of A, and we look at the jth component of it, what's that equal to? So I write parentheses with a subletter that indicates the component of a vector. Like, so this is like, I need two indices for a matrix because you have to distinguish which row and which column, right? But if we're just dealing with a row vector or a column vector, there's just one index on it, right? So here, the I and the J aren't really an index, they're a label. In this context, it's just saying I'm looking at the jth column, I'm looking at the ith row. Okay, so what's the ith component of the jth column? Well, it is Aij. And the jth component of the ith row is Aij. So, for example, like let's be specific here. If I want to look at row 1, component 2, that's this guy right here, A12, right? If I want to look at column 2, component 1, that's also A12. So that's how this notation works. It's sometimes helpful to have a index-based definition of the column or the row, right? Because if you can work at this level of notation, then it doesn't oblige you to write out all of the components every time you make an argument, right? Okay, so there's that. So next up, definition. If A and B are both in m by n matrices, then A is equal to B if and only if Aij is equal to Bij for all I and j. And here, let me unwrap that. What do we mean by for all ij in this kind of context? What's that indicate? What does this mean? This means all of these cases that we already listed up there, right? It has to be every component of it. So for two matrices to be equal, they have to be equal in every single possible component. This is just like you already learned for vectors, right? Maybe you didn't. I don't know. How many people have seen vectors in a course? So anybody know? Okay, so you have some sense of how this works. It's just like a vector. The only way for the two objects to be equal is they have to be equal in every component. So what this means then, among other things, is let's look at an example. So like, if I have A is equal to 1, 2, 3, 4, and that's equal to, x squared, yz, what's this tell me? I get 4 equations, right? I get 1 equals to x, I get 2 is equal to x squared, I get 3 is equal to y, I get 4 is equal to z, right? So what does that tell me? Yeah, there's no such matrix, right? So this is impossible, right? No can do, not possible. See, because x is equal to plus or minus the square root of 2 there, which is not equal to 1, right? So there is no such matrix. All right. So kind of a silly example, but you can write a matrix equation. If I write a matrix equation, I get not one, but a bunch of equations all at once, right? All right, moving on. So definition. if A is in Rm by n, then A transpose is in Rn by m. And A transpose, parentheses, Ij is equal to A Ji for 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to n. Right. Notice that the meaning of the row and the column indices are flip-flopped as you go from the matrix to its transpose, right? And what it means sort of schematically is that we change each row to a column and we change each column to a row if we go from a matrix to its transpose. So let me just give you some examples of this. So if we had like the vector, which is a row vector, 1, 2, 3, then V transpose is 1, 2, 3, right? If I have, the matrix A is 1, 2, 3, 4, 5, 6, a 2 by 3 matrix, then A transpose is 1, 2, 3, 4, 5, 6, a 3 by 2 matrix, right? Here's another one. I could have X is equal to 1, 3, 5, for instance. That's a column vector, right? Let me remind you, we have another notation for that, which is this, right? That's my sneaky, hidden, implicit column notation. In this case, we have X transpose is actually 1, 3, 5. All right. So enough of that. I think everybody, pretty much nobody has trouble with transposition, right? That's not a big deal. So our next definition is if A and B are elements of Rm by n and C is a real number. All of these definitions I'm giving could equally be well done for some other choice of field, right? You could do these for complex numbers, or even if you wanted to work over like, integers mod 2 or something. But we won't do that in here. We're going to keep it real. So here, what if we wanted to define, we can define A plus B, right? And also, a constant times A. Notice that because two matrices are equal, if and only if they have the same components, to define the sum of two matrices or a scalar multiple of a matrix, it suffices to say what happens to the ijth element, right? So this is Aij plus Bij and Caij. So the left-hand side here, I'm talking about the ijth component of the object we're defining. On the right-hand side, we're just talking about, real arithmetic. Now, I should mention here, guys, these rules specialize if we're talking about like a row or a column vector, right? So if we have like V is an element of, say, R1 by n and W, then if we have like W plus V sub I, it's W sub I plus V sub I, and CW is CWI, right? And so what I'm trying to say is the two indices are only needed if we're actually dealing with a matrix that has more than one row and more than one column at once, right? So, if we have, let's say, X and Y in Rn by 1, oops, my bad. Now, Rn by 1 is also by our custom equal to Rn. So Rn for us is column vectors by default. So X plus Y sub I is X sub I plus Y sub I, and Cx sub I is Cx sub I. So this is row vectors, column vectors. I suppose there's one other case, but we hardly ever talk about it. What if you only have one row and one column? What's a 1 by 1 matrix? It's just a number, right? So we won't bother with that. But that can happen, right? That is a special case of a matrix, and there are matrix products that we form that end up being there. So I really don't have much to say example-wise about this. I think none of us are going to get stuck on this. I will say that there's one special matrix that we should talk about just a bit, which is the zero matrix, right? So what's that going to be? So 0, the ijth element of it is equal to? 0. 0, right, yeah. So that's the zero matrix. So we can rattle off some properties of matrix addition here right quick before I get on to the next thing, which is a little bit more interesting. But so how about this? If we have a plus b, can you tell me anything about it? What's it equal to? What if I have a plus b plus c? What if I have like c times a plus b? What if I have 0 times a? Or c times the zero matrix? Can you tell me something? A plus b is equal to what? B plus a. Very good. Matrix addition commutes. So we can do that. The next equation there, a plus b plus c, I usually say, well, that makes sense, right? Which is a kind of glib way of me saying that matrix addition is associative. See, if matrix addition was not associative, then we'd need these parentheses, wouldn't we? Because it would matter which ones that you added first, right? So it's commutative, associative. It plays nice with addition. See, c times a plus b is ca plus cb, and there's another one, right? C plus d, little d, times a is equal to ca plus dA. We sometimes forget about that, but this is for C and D in the reals. So scalar multiplication distributes both across matrix addition, but also across scalar addition in this way. And if you have 0 times A, you get the zero matrix. If you have C times the zero matrix, you get the zero matrix, all right? I don't prove much in here, but since it takes me all of about 3 seconds to prove one of these, let's do it. How would I prove that A plus B is equal to B plus A? I take A plus B, right? I look at the ijth component of it. That's equal to, by definition, Aij plus Bij, right? By definition of matrix addition. But by properties of the real numbers, we know real numbers do what? They commute under addition. So this is Bij plus Aij, which is equal to B plus A Ij. And therefore, A plus B is equal to B plus A, since the above holds for all Ij. So this is like a typical way we prove a property of matrices. We look at the ijth component on the left-hand side, and we prove that it's equal to the ijth component on the right-hand side. And in so doing, we proved the matrix identity. And all of these ones really follow immediately just from the definitions of matrix addition, scalar multiplication, and the corresponding properties of real numbers. All right? Mm-hmm.
How can we tell if we write 0 if you're talking about
Context.
0 or just context?
Yeah, just context. We don't know which 0 it is until we look at the context, because you're right, it is a vastly degenerate notation in the sense that I say 0 matrix as if it's a singular thing, but the truth of the matter is that's an infinity of things, one for each different sized matrix. Absolutely. Yeah. That's true. You caught me. So next up, there's actually something to learn here. More so. I'm not saying that there's nothing to learn here. I'm just saying that I think everybody here can learn this stuff without breaking a sweat, right? Matrix multiplication it requires a little bit more attention, So first of all, context on my previous property here. In order to add these matrices, they had to have what? In order to even ask the question, can you add them? What do you need to have? They have to be what?
Same size.
Same size. So I didn't write that on the board, but it should be understood. That's the one thing I really should have emphasized, is in order to add matrices, they must be the same size. Matrix multiplication, a little bit more fussy. So here's the definition. Let A be in R m by n, and B be in R n by p, then the product AB is an element of R m by p and is defined by A, B, ij is equal to the sum k equals 1 to n of A, I, k, B, k, j. A, I, k, B, k, j. Now, of course, this assumes that, there's special cases to this formula I will talk about momentarily. And the special cases, unfortunately, in my current version of the notes, they're not actually typed out. So I'm going to write them on the board for you guys, because it does matter, the special cases. But this is the notation we need in the case that basically this is basically for both m and p greater than 1. If m and p are both greater than 1, then the I and the j indices, they both range over more than one value, so we really need them. Okay, on the other hand, if I have, let's call it a row matrix product, we can write the formula V times A, the jth component of it, is equal to the sum k equals 1 to n of vk a kj. So you notice there's no I component here. Let me see here. Just to make sure this makes sense, let me talk about the dimensions. So for the general one, like up here, we have, you notice the pattern? We got like m times n times p gives us an m by p. This one here, the situation is 1 by m. Oh man. Well, I need to fix this. Just give me a second here. I'll fix it. Times m by n, if I'm sticking with my notation, gives me a what? A 1 by n. All right? So if I do these carefully, the summation should be over the numbers which match up in the the row and column dimensions that are up against each other. So you see this I said A was m by n up here, right? So I'm kind of stuck with that m there. So the formula I have written by hand on my notes is not consistent with my choice of A. So this n cannot stay, right? This has to be a what? See, I'm summing it over the first index of A, which is a row index that ranges from 1 to m. So I have to put an m here, not an n. That's a row matrix product. And so this is, again, a row. It's the jth row, actually. A matrix column, rather. So it matters which one comes first, all right? Matrix column product. There we'd have like A times X. The ith component of it would be the sum k equals 1 to n of A, I, k, x sub k, I believe. That's a matrix column product. So again, just to keep track of the counting here, I have m times n times an n by 1, and that's going to give me another m by 1. So let me just put it in words. The row matrix product is a row. The column matrix product is a column. So what's the other thing that could happen that actually matters? So this is, I'll put it in words over here. So VA is row. AX is column. What if we had not a genuine matrix, although, I mean, okay, so this is the thing. A column is a matrix. A row is a matrix. Even a number is a matrix in a certain respect. It's a 1 by 1 matrix, right? So I have to be careful with what I say about that. But, so what if I have a row column? Can I do that? So like 1 row, n columns by n columns, 1 row. Wait a minute. N rows, 1 column, right? I could do that, couldn't I? So if I had like, you know, V times W, what would that be equal to? Sum k equals 1 to n of V sub I. My bad, V sub k, W is k, right? What's the other thing that could happen? Although I think this is already technically covered by the previous formula, but notice that if you had column times row, you know, you just flip the script here, WV, then the ijth component of that is what? So here I've got, you know, my bad, I shouldn't use WV. They could be different sizes. Let me try this again. Not W and V, but like X and Y, I guess. All right, so I'm talking about a n by 1, my bad, I'll get it eventually here, an m by 1 and a 1 by n, let's say. You could make these whatever you wanted, but the point is, there's no, see this? Previously, whatever number is here, we had to sum over those components, right? Like this one, I didn't write out the symbol. Oh, it's up here, right? Sum over n, right? This one, the m's matched up, sum over m. This one, again, the n's matched up, so sum over n, right? This one here, the n's matched up, so sum over n. This one, the ones match up. There's no sum. This is just x sub I y sub j, I believe. I gotta think about that for a second here. Make sure I'm not deceiving myself, you know. Yeah, I think that's right. So, all right. So there you go. That's your definition in all possible cases. There's a lot of cases there, isn't there? So now I'm going to spend the next, well, the rest of class probably just illustrating by example how we actually multiply matrices. All right. And I'll probably just start. I'll start with some of those exceptional cases. So, where am I? Example 3? So, example 3, let's do a row matrix product. So, if I had like, actually, I'm going to do the matrix column first because it's more natural to me. So, if I have the matrix 1, 2, 3, 4, and I multiply it by the vector xy, right? No connection to the xy up here, right? This is a totally separate use of xy. Anyway, so here x and y are scalars. So I've got a 2 by 2 times a 2 by 1. And what this gives me is 1 times x plus 2 times y and 3 times x plus 4 times y. Or if you like, we can just simplify that as x plus 2y and 3x plus 4y. So that's an example of a 2 by 2 times a 2 by 1, giving me another 2 by 1. On the other hand, if I had C1, C2, like this, times that same matrix, 1, 2, 3, 4. All right, the way it works is I get another row vector. I get C1 times 1 plus C2 times 3, comma, C1 times 2 plus C2 times 4. I'll rewrite that just one more. C1 plus 3C2, 2C1 plus 4C2. This is how we do a row times a matrix. So do you guys, who knows what a dot product is? Some of you do. Who doesn't know what a dot product is? Okay, so let's talk about that. So this up here is actually an example, up on the top corner here, this is an example of a dot product. Dot product is, let's see here. I'm out of space here, so I better move over. So we can take two vectors and take their dot product and get a number. So let me give us a sort of it may be useful to us just to give a standalone definition of the dot product. So let me be a little bit sneaky here. This is probably not in the notes, but definition: if A vector and B vector are two n-component vectors, then A dot B is A1 B1 plus A n Bn. In other words, it's the sum k equals 1 to n of A sub k, B sub k. So this is the dot product. I want to, just for the sake of having a nice language, allow us to take the dot product of row vectors with column vectors, row vectors with row vectors, and column vectors with column vectors, right? Provided they have the same size, right? So in this wild world of hybrid notation, like my VW. So if I have, let's see here, example 4, I suppose. Suppose I have V is 1, 2, 3, and my W is column vector -1, 0, 7. All right. Then I would like to allow us to do V dot W is equal to 1 times -1 plus 2 times 0 plus, 3 times 7. Which is what? I don't know. 21 minus, I guess it's 20, right? So notice that also is equal to, by the upper right hand, up thing in the upper board over there, that's equal to VW as well, right? On the other hand, let's flip around. WV, 1, 2, 3 times -1, 0, 7. The way this works is very silly. But you do 1 times -1, 0, 7, and then 2 times -1, 0, 7, and then 3 times -1, 0, 7. Those are scalar multiples. Let me write that out. So what we got is -1, 0, 7, -2, 0, 14, -3, 0, 21. That makes sense because what we're doing is we're multiplying a 3 by 1 times a 1 by 3, right? And that gave us a 3 by 3 matrix. All right. So I'm front-loading this lecture with kind of the weird examples. I'm going to now focus more on like genuine matrix products. If I can here. I guess one more weird example. What would it look like? I mean, it's not that weird. If I did W transpose W, what would that be? We'd have -1, 0, 7 multiplied by -1, 0, 7, right? Row vector times the same vector but as a column. And so the way this works, so watch this, guys. I take my hand, right? And I actually imagine taking this and sort of just tilting it sideways and then kadunk like that. So the -1 multiplies by the -1. The 0 multiplies by the 0, and the 7 multiplies by the 7, and I add those. That's the definition of dot product. So I like -1 squared in this case, plus 0 squared, plus 7 squared, also known as 50. All right. Let's see here. Let me erase these. Yep.
When you wrote WV, you switched the matrices in the example before.
This one?
Yes.
Oh yes, these are not equal. Thank you. Yeah, that's on purpose. These are not the same. Thank you. That's a helpful comment. These are not the same. Actually, that's my point, is that when we multiply one way, we get a number. If we multiply a different way, we get a matrix. Are these commutative? No, not even the same type. Far from it, yeah.
But you can put the, like, V is 1, 2, 3, and you have it before the W. That part is commutative, the multiplication part of the matrix. You could put that matrix 1, 2, 3 on either side of the negative 1, 0, 7 expression.
No, actually I cannot. Excuse me.
Because like W times V, and then you have V equals V times W. Is that, see what I'm saying?
Well, this is the dangerous thing about this notation, is that this is not equal to W dot V, if that's what you're asking. W dot V is a number. It's 20. I'm not sure I fully processed your question.
I was just asking if, like, it's supposed to be W times V, so I was thinking that it would...
Did I? I'm sorry. You guys are telling me that I haven't been faithful to my W.
To the order, yeah.
My W was this column vector, and I'm not writing it as a column vector now. So
does that
that's...
change anything, or does
Yeah,
it
I mean, I'm not being... Oh, man. I see what you guys are saying. I'm sorry. Thank you. Just a second. I have swapped something in my mind and when I wrote something down. Give me a second. I'll unravel it. All right. If V is 1, 2, 3, so what I should say is that this is VW right here, right? This is VW.
When you did the multiplication, like that was WB, it's just the first, like, WB equals negative 107 times 1, 2, 3, and then after that it's all right. I think it's just that first step.
Right here?
Right after that equals sign.
It's fine, right? Yeah.
Or
No?
between.
Oh, yeah. I'm
Times and the column vectors, like that's all W times V. But you
Oh,
have a 1 by 3 matrix times a 3 by 3 matrix.
let me... Yeah, so, okay, fine. Yeah, is that reasonable? That's a good question. So you think that's not reasonable? This right here is nonsense.
Yeah.
You can say nonsense, it's fine. So this is, what size matrix is this?
1 by 3.
1 by 3. What size matrix is this? 3 by 1. This is nonsense. Thank you. So what I meant to do, okay, so there's one step here that needs to be fixed, which is this one right here. That just needs to be turned over. It's what you're telling me like 5 minutes ago. So let's do that. I'm sorry, guys. You know, I try, but this is 7. I mean, wait a minute, 8:15. And this is what happens when I teach at 8:15 every time. So there you go. Now, not crazy. 3 by 3 matrix. Right, 3 by 3 matrix. Nothing changes, it's just that. I should write in the order I actually did it. This down here is okay, because I actually transposed W, wrote the transpose of W, wrote W. That's fine. All right. So it's just that. Okay. Come on. This stuff is not hard unless you find a way to... Well, anyway, my goal is to confuse the students, so mission accomplished. Let's see here. Okay, so moving on. Let me derive a formula for us right quick, and then we will use it with a vengeance on everything that follows. So check this out. AB, I'll do it. how about this way? So if we have row I of A dot product with column J of B, how would that work? That would be the sum, and I'm going to assume A and B have the same dimension as like in my definition. So A is m by n, and B is n by p. So that makes both of these n vectors. Okay, that's what they're both n vectors. So k equals 1 to n of row I, the kth component of this times column J of B, the kth component of that. What did we learn about the, we learned how we could define those, right? This was what? This was the sum, k equals 1 to n. How'd that go? What was the deal? Column, the jth column, the ith component of it, it's aij, right? So this is a, oh man. Seriously? Oh, I can't. Oh, don't let me do that. I'm just flipping row and column in my mind just now. I am my own worst enemy. So to start with, we have aik. Just going back to what we did earlier in the class in terms of like identifying what the formula is for the ith row. And on the other hand, this one, flip the script because it's column. So that's like bkj, right? But what is that? That by definition, folks, is abij. So what this is a prescription for how you can calculate matrix products, right? So like this gives us a theorem, which I'll write sort of like this. To find the 1, 1 component, we take like row 1 of A dot column 1 of B, and then you get like row 2 of A dot column 1 of B, and so forth. Row M of A dot column 1 of B, and so forth. Eventually down here you've got like row M of A dot column N, not column N, column what of B, according to our current setup. B was what? N by P? How many columns are there then? P. There's P columns, right? So this should be column P. Just to remind you what we're doing, A was what? It was M by N times N by P. So the answer over here should be, again, an M by P matrix. All right. So what this means then is if we can calculate dot products, then we can calculate matrix products. We just have to do it in the proper order. Uh-oh. I highly recommend not breathing in the juice. Not good. Not good. All right, so let me actually multiply two genuine matrices here, and then we'll be done for today, I suppose. What example are we on? 5? Yeah. So suppose I've got the matrix 1, 2, 0, 8, and I'm going to multiply it by the matrix, let's see, 2 by 2 by, and I won't multiply it by, let's say 2 by 3. So 2 by 3 looks like what? 2 rows, 3 columns. So we'll do 4, 0, 1, minus 1, 2, 6. All right. So what we do is we do 1, 0, dot 4 minus 1. 1, 0, dot, oh man, good grief, what's wrong with me? Sad. Let's see here, so let me just write down the numbers. We have 1 times 4 plus 2 times minus 1. And then we have 0 times 4 plus 8 times minus 1. Those are the dot products there. Then next up, we do 1 times 0 plus 2 times 2. And then 0 times 0 plus 8 times 2. Finally, 1 times 1 plus 2 times 6. And 0 times 1 plus 8 times 6. Notice that the column, like this column here, figures into these numbers. This column here figures into these numbers. There's a really nice pattern that we'll need to understand more deeply as we go on in this class, but that's it right there. And of course we can, we shouldn't leave it like that. What do you got? 4 minus 2 is 2, minus 8, 4, 16, 13, 48, right? There you go. Is that equal to, so if this is A and this is B, is this equal to BA? This would be a what? 2 by 3 times 2 by 2. No allowed, right? Dimension mismatch, your calculator will tell you. So if you guys haven't seen the video I posted Saturday to help you with your homework, make sure you look at it. It does have more or less very strong hints for some of the homework. And don't forget the homework is collected Wednesday. So anyway, I guess I'll shut up for today. I do have an attendance sheet for you guys since you're here. And if you want, I have some Trump stickers.
Yes.
Although I only have a few, so get them while you...
I need that.
Let's see here. I have more Trump stickers in my office if you really desire one this day.